Okay, so when I finish quickly the thing that I was discussing last time about the identifying the part of structures that can be generated by adjunctions, and then I'll start talking about the last thing that I want to cover this time and next time about comparisons between models of generative linguistics and what is happening with large language models. So I mean, just before just a reminder, send me your preferences about your presentations, and I'll try to put together a schedule in the coming days. So you just choose whatever you want. I mean, some of the papers on the webpage are like more math papers, some are more linguistic paper. You can either choose one type or the other, or a combination. It doesn't have to be like one paper. You can choose things from different things. So it's up to you. I mean, just send me your preferences, and it's sort of first come, first serve for what have already been assigned. Then I'll keep an update of the presentations that have been assigned on the page. Okay, so let me just finish discussing briefly this story here. So what I was saying last time is that you have this kind of chains of adjunctions that you can form, and typically like a very simple chain of adjunctions would be a tree that looks sort of comb-like. And it might start with some other structure and then that add this kind of comb-like structure that's a simple chain of adjunctions. But more generally, you can have adjunctions where the things that you add themselves can have some structure, so they're not just these comb-like things that could have like some trees and comb-like things interspersed with other structures. So the question is what one can characterize, like among all the possible planar trees, which ones are of this type in some sense, of which region they occupy in some parameterizing space of planar trees. So one way to think about how to characterize this part of the structures is in terms of, so this is also, I'm talking about this also as an excuse to introduce some of these structures of planar trees, which are useful for various reasons. And so one way to think about it in terms of the Tamari order, which is a way of arranging your planar structures on a given tree, so on a given set of leaves. And so you fix an ordered set of leaves, and you look at all the possible planar trees with those leaves. And of course, these sit at the vertices of the associahedron and leaves. And the thing is that you can take this one skeleton of the associahedron and put some orientations on the edges that define a certain order structure. So it's a partial ordering where two things are in the ordering if there's a chain of oriented edges between them. And the idea is that you put an oriented arrow between two planar binary rooted trees if they are obtained by moving one edge from right to left across a vertex in the tree, which actually does correspond to one of these exchanging of bracket of a lack of associativity rule, which is two nearby vertices in the associahedron, except now you order them in the direction that corresponds to this switch from right to left. Okay, so if one looks at the Tamari lattice in this sense, we'll see is that the comb-like trees are the extremals of the Tamari order, into the case of 4 and 5 leaves, and that everything else is sort of populating the areas in between, and they're more or less close to one of these comb structures. You can think of this ordering as telling you how far you are from these very simple comb structures. And there's some operations that are sort of related to properties of the Tamari order. And these are the sums of trees. And they are based on these operations of sliding over and under that I already described, where you slide one tree along the other one until you reach the leftmost end, and then you place it there, or the rightmost end and place it there. And these two operations have a specific relation with respect to the Tamari order, regardless of which trees you use. They're always in this ordering with respect to the Tamari lattice. And Loday defined this non-commutative sum of trees by taking the union of all the things that are in between these two in the Tamari order. And it's an associative or non-commutative addition of trees that distributes over unions. And these were the examples that I showed at the end of last time. If I make this sum in one order or the other, you get these unions of trees. And the next observation that they made is that you can think of this sum as a combination of two parts. It sort of splits the plus sign as its left part and its right part in this way. And each of these two operations can be defined recursively in terms of this total sum, but on either the left part or the right part of the tree, given that the tree is planar, you can always write it as a left subtree merged with a right subtree and vice versa. And so these are just recursively defined in terms of this sum on the lower level, applied either on the left or on the right. Okay, so why is this useful? Well, because one can start with this very simple, the simplest possible binary tree, which is just a cherry tree, and then you start adding it to itself. And when you add it to itself, you have these two halves of the sum operation that just give you exactly these elementary adjunctions, elementary COM trees. And so the elementary COM trees, you can think of them as just iterating the either left or right part of the sum a certain number of times of this basic binary tree with itself. And so one can think of this as like the head initial chain of adjunction or the head final chain of adjunction, respectively. So this means that these elementary adjunctions, there's a way of describing them in terms of what happens with the Tamari lattice and the associaedra. Well, if you add this further chain of an adjunction, so if you do something like here, you start with this and you add a further adjunction either on one side or the other. Of course, you move from one associaedron to another one because now the number of leaves has grown. So you're not moving within the same associaedron. You're moving from the n to the n plus first associaedron. And the things that the n plus first associaedron can be identified with the cylinder over the nth one, where the edges that you're adding are corresponding exactly to the intermediate steps that exist between. So the two extremal vertices would be the ones that when you add your tree to another, to one of these cherries, or one way, or you add the cherry the other way. So it's like one of the other operations. And some of the edges have intermediate things when there are non-trivial intermediate things in the Tamari order of Kn plus 1. Like in this case, you have one intermediate tree that's related strictly larger and strictly smaller than the other one. And in another case, you don't have anything. And so one sees here that the associaedron K4 is a pentagon with this vertex included. But is also realized as the K3, which is simply a segment times an interval, except the interval has an intermediate vertex in this case. Okay, so this is actually a general fact. You can always parameterize the planar binary rooted trees on n plus 1 leaves in terms of the planar binary rooted trees on n leaves by performing one sum in the Loday sense with this particular cherry tree. And the segments are the number of vertices that you're adding in the new associaedron comes from the number of intermediate steps that you have in the Tamari order between these two. Okay, so given this fact, if I start with a given tree and then I perform a chain of these simple adjunctions that adds a comb-like structure to this tree on one side, so this is like the simplest chain of adjunctions, then it means that I'm passing from a vertex of some Kn association to a vertex of the Kn plus capital N, which is the number of adjunctions that I'm making here, which I view as a product of the Kn with a cube of dimension N, which has a number of intermediate vertices, but still. And the things that these structures that I obtain, this chain of adjunctions, is located at like the topmost vertex of this additional cube. So it means that it occupies a stratum which is of very high codimension inside this larger associated. And so this is a way that you can think also of more general type of chains of adjunctions where you allow some of these to have some additional structure, but you can still think of it this way, like if you make a chain of adjunction where some of the things you like have some further inner structure as trees, you will still get things where you decompose the associatron that you get to into parts of lower dimension and cubes that correspond to the number of simple adjunctions that you have. And so the conclusions that you can characterize, which part of the overall associatron of the full dimensional number of leaves that you have are occupied by this kind of chains of adjunctions, and by specifying exactly the codimension, with which strata, which codimension you're going to end up in the higher dimensional. So this is like a way of answering. There's a this kind of question about the what type of characterization you can give of which structures can be formed by chains of adjunctions, so sort of formulated in various places, and this is like this construction of Loday that you can use to answer this question. Okay, so this is just an example of application of some of these ideas about structure, geometry of trees and associaedra, to answer some questions that exist in the linguistic literature independently. Okay, so this is one last thing that I wanted to mention, because I had spent some time on this associaedra and so on. And so now let me get to the sort of final topic that I want to discuss. Okay, so here we come to what is going on. What I talked about. So about generative linguistics, I talked about all the time up to now. And now there's something else that is fashionably going on, which is the use of language in something else that's called generative in a very different sense. I mean, generative artificial intelligence and large language models. So of course, at some point I have to talk about this, because we would all like to have stories that have a happy ending, but in real life, unfortunately, that is never the case. So let's get down to see what is actually going on here. So okay, first of all, that one thing that's important to realize is that if we want to talk about language in large language models, you have to actually take a very deep dive backward in time by about 80 years. So this is the first observation that I want to make is that technology is not theory neutral. If people are trying to convince you that technology is theory neutral, they're either delusional or it's propaganda, or both. So the first question that one needs to ask is like, what is the actual theory that is behind the technology that you see? And so this has a very precise answer in the case of the large language models. And the theory is actually about 80 years old, and it predates the introduction of modern linguistics. And so it's 80 years old and it's 70 years obsolete. And this is actually the theory that Zellig Harris developed in the mid-1940s up to mid-1950s. So what does that consist of? I mean, Zellig Harris was a very famous linguist of the time. He happened to be Noam Chomsky's PhD thesis advisor. And at the time, this was one very well-developed model of language. And so it was what was called structural, distributional, distributional structures or distributional model of language. And so, first of all, it entirely viewed language as strings of words rather than as structures, as is the view in all of modern linguistics. And it was primarily based on the idea of distributional properties of text included into longer text, pieces of text included into longer text. So distributional properties in the sense of probabilistic statistical distributions of inclusions of strings of text inside other strings of text. So in all this, part of the idea of this model was that syntax is seen primarily as this kind of probabilistic distribution of relations of how strings of text are included into each other. So there is no attempt, intentionally no attempt to actually model syntax as its own structure, especially as its own computational structure. And all relations, in what we, in modern linguistics call syntactic structures, would simply be described by probabilistic relations. So no kind of abstract, algebraic structural relations. And of course, we know that language follows certain rules of how you modify sentences and so on. This is sort of undeniable even by the most extreme proponents of this kind of probabilistic approach. And so part of the model that Harris was proposing was that there should, whatever rules of modification of sentences are, they are just to be extracted in some kind of mechanical algorithmic way from this data of probabilistic distribution of inclusions of text. And this actually, I will come back to this idea because it's of this kind of mechanical way of extracting, whatever rules you want to describe about language, because it is actually very closely related to a particular point of view now in the theory of transformance in large language models, which is the idea of circuits and the idea of mechanistic interpretability, which I'll come back to. So, as I said, this is a view of linguistics which was dating back to before the main paradigm shift of modern linguistics, which happened in the mid-1950s. It's of course an intuitively simple model, which also happens to not be very accurate. I mean, it's an interesting point in the sense that if you rewind back the clock of a scientific field by almost a century, you find something that looks very different. Like if you rewind the clock of theoretical physics by a century, people didn't even know the existence of neutrons. The neutron was discovered in 1932. Of course, it was the blink of an eye from there to the first atomic bomb, but up until that point, the idea of what the atom looked like was something completely incompatible with what we know today. So if you were to do you could have the best possible modern technology to do models of physics, but if your physics were wind back 100 years, you wouldn't be doing very interesting physics. Okay, so this is one observation. Okay, so something more about the historical context of this theory of language that is directly underlying the approach, the technological approach that we see now. So this point of view that Zellig Harris proposed was actually coming from a previously very widespread idea and tendency, which was behaviorism in psychology. And that had exactly the same idea. So behaviorism in psychology had the standpoint that you can only statistically observe behavior. You completely renounce the idea of creating theoretical models of the mind. So this entirely predated, again, all the modern development of cognitive science and neuroscience, which is about actually trying to understand the functioning of the mind. This was just the idea that as a philosophical standpoint, you don't want to do that. All you want to do is just observe statistical patterns of behavior. And this was a point of view that was extremely widespread in psychology, and that spread from psychology to several other fields that had to do with thinking about the mind, including linguistics. The change of scientific paradigm happened in 1955 with this long book that was actually the PhD thesis of Chomsky in 1955. It happened to be published only in 1975, and because indeed it gave rise to a kind of cataclysmic shift in perspective in how to think about linguistics as a science. So this is a very long text, and a lot of it is dedicated to criticizing this model of Harris and giving both empirical and theoretical evidence for why it doesn't work. And one of the main points of criticism is about the fact that this distribution of viewpoints is not suitable for seeing something like the structure of syntax, because if it intermingles too much the semantic side and the syntax side, which in the modern theory are decoupled. And the idea in the modern theory, as we have been discussing for all the rest of the term, is that there's a computational mechanism of syntax, and then there's a mapping, there's an interface that maps it to parsing that takes care of semantic interpretation. But these two things can be analyzed and should be analyzed independently because they obey different kind of rules and different kind of mathematical structures and so on. And the things that if you put everything on these occurrences of distributional statistics of text in languages, what you see is the occurrence related to the semantic likeness. But for example, syntactic structures that are the same identical syntactic structure can manifest themselves with completely different probabilities according to whether the corresponding choice of words is probabilistically correlated or more or less probabilistically correct. And the other point is that if you want to have something where you can conduct your investigations according to what the scientific method should look like, you need theoretical hypothesis and verifiability in data, rather than just statistical correlation between data, where doesn't give necessarily rise to a theory. I will actually come back. So I'm not saying with this that you cannot do useful things with this Harris point of view. I will actually give you a specific example of something useful that was done historically with this point of view of Harris, which is quite interesting. But I'm just saying that there were a lot of things that as proposed as a model of language it doesn't give you a theory of language, not in the modern scientific sense. Okay, so this. So fast forward 80 years from from this, we have the new phase of behaviorism, which is transformers. Well, most of the time they actually look like this. But so, okay, I'm gonna talk about how these new clothes of behaviorism actually function. I'm gonna do it in a couple of levels of detail. So first, I'm just gonna give some very rough description of some of the main aspects, and then we're trying to get a bit more into the actual thing and looking more closely at some of the actual behavior of the internal functioning of these things. Okay, so first look, kind of not too detailed, but just trying to capture some aspects that actually have some relevance to what we were discussing in our models of syntax semantics interface. So the key part of the structure that I want to look at is this attention module, in particular self-attention modules, and I'll come back to discuss these structures more in detail in a moment. But I want to extract some key features. So there's a key ingredients are 3 linear transformations. So of course, linear algebra is by its own nature excruciatingly boring. So one has to somehow put up with that. I don't know, a lot of modern mathematics is trying to escape the deadly boredom of linear algebra by trying to make it into something more interesting, like when you are desperate about you just imagine yourself being in some abelian category, and then things starts to look a little more bearable. But here we are down to actual linear algebra. So there are like 3 matrices. that's the essence of transformers, 3 matrices. So these are, let's call them queries and keys and values. And so in a sense, we are back into the idea that our semantic spaces are this very simple model of semantics that are based on vector spaces, and where the proximity between vectors is somehow a proxy or a way of measuring the semantic proximity between them. Okay, so these are the ways of encoding. So you can think of at this level of generality, we can think of queries and keys as being, in a sense, looking for vectors, words in the sense of vectors in your semantic space that are structurally related to your given vector, and in 2 ways. In a sense, those that are called by your given vectors, and those that will be called for by your given vector. So, you can think of this in a sense as being analogous to this notion of semantic probes that I described in the model of the syntax semantic interface that I was discussing before. So you can think of having an assigned vector in your model, vector space model of semantics, and your query vectors are a certain set of probes or semantic probes associated to this vector by a linear transformation. And queries in the same sense, you can think of them as being in the dual vector space, where if you want to identify a vector space with dual, so it's a finite dimensional, but technically would be in the dual vector space, and would be probes that you evaluate on your. So one of them is probes that your vector generates, and another are probes that you evaluate. And so there is this these dual roles of your given vector as something that either receives probes or generates probes. And in additional, there is a value vector, which is some representations in some, here is where you can allow for either reducing dimensions, by projecting on some lower dimensional part of your very large dimensional vector space, or you can add dimensions in which you can store other information in the course of the computation. So it allows for some varying of dimensions. So I'll be more precise later. So this, as I said, this is kind of a first vague description. I'll come back to that. And so you have a certain string of text, which is divided in general not into words but into tokens. It can be not coinciding with words, but let's for simplicity again assume that these are like the lexical items that we were discussing. And you have this. So there are two different types of architectures, and one that. So first of all, you have some kind of variable that we keep into account the ordering, the position, so the ordering of words, since you really think of this text as being ordered text. And you have architectures that are bidirectional with the unidirectional that will look only at things that precede a certain word or will search in different directions. So this depends on the task you're training for, whether it's predicting the next token or it's masking certain parts of the phrase and wanting to predict the parts that are hidden. That depends on the. But essentially, the key operation in these attention modules is to generate some probabilities. And the way you generate some probabilities is by taking these queries and keys vectors, pairing them with each other. So pairing them means evaluating their correlation, their proximity in your semantic space, or the amount of relatedness in your semantic space. And then sparing this out as a probability distribution by this kind of softmax operation. And this creates weights, which are probability weights. There's some kind of rescaling factors, there's some kind of temperature factor that I'm not discussing, but basically your attention matrix is constructed in this way. It takes care of assigning these probabilities. And your output then is taking this weight, these vectors, these value vectors, and weighting them according to this probability distribution. Okay, so one observation first is that this, which I've already said, is that in this model, the linear order relation of text is important. The continuations of text, so inclusions of text into subtext into text is important. And you're generating probabilities of the next outcome, which sort of is generating a distribution over inclusions of text in the sense that I was describing a moment ago. And however, the first thing that one of the first things that I want to discuss is that although this is entirely based on this semantic proximity between these vectors in a vector space model of semantics, you do see this kind of image of syntax inside semantics that we have been discussing in general for any sort of model of syntax semantic interface. So yeah, let me mention one thing that I'll come back to later. Usually you have multiple of these head attention modules in parallel. So each one you call it an attention head. So there's a slight conflict of notation here because of course we have a different meaning of head in the syntactic sense. And so because I'm gonna in a moment use that meaning of head, for now, I'm going to forget about this multi-head, and I'm going to just, anyway, for the purpose of what I'm saying now, it doesn't matter. You can have just one. The structure is the same. I'll come back later to this more. Okay, so for now, let me just set this aside to avoid terminology confusion. So this would, in principle, you would have one such thing for each of your parallel attention head, but I'll momentarily set that aside and come back to it later. Okay, so far we just have this type of structure, right? You have your tokens, let's say lexical items, but more precisely would be the tokenization of words. But each one of them gets passed through 3 linear transformation, produces queries, keys, and values. Queries and keys are paired to form these probability distributions, and the values are weighted by this probability distribution, and that gives you the output. So this is the very basic structure of what is going on there. Okay, so what is actually happening, right? So the one observation is that so far there've been quite a bit of empirical testing about the language produced by large language models. And there are conflicting results about the handling of syntax by large language models. So I'll come back to discuss some of the results more precisely. Okay. But one thing that seems an interesting observation, there's a already some years ago in is a paper that observed the fact that you seem to be able to recover some of the syntactic structures, so of the actual parse trees of syntax from the weights of these attention modules. So the weight, I mean, these probability distributions generated by attention module. So this seems to indicate, I'll say more in a moment, that there's an image of syntax that is detectable inside these probability distributions that are generated by semantic relatedness. And in a similar way to what we have seen, that you get a sort of embedding of syntax inside semantics. And of course, there's some ways in which manifestly this process of acquisition of the calculator of syntax through this embedding inside semantics seems to function very differently from the way that our acquiring of language functions, in the sense, for example, that manifestly there is what linguists call the poverty of the stimulus in our learning of language, in acquiring language through human learning, versus what one can only call the overwhelming richness of the stimulus that is fed to a large language model for training. And I mean, one can go down all separate paths about discussing things like the cost of this, not just the cost in terms of money, but the environmental cost. You can look up the water consumption of the training of GPT, in terms of billions of liters of fresh water that just went into that. So of course, there's a natural question to ask whether such a thing is, such a cost is necessary. And whether it's not necessary or not is necessary partly depends on the fact of what is the theory behind these things. Are we how are we modeling the acquisition of language? Okay. But even without the practical consequences as a question in itself. So I'm going to discuss in a moment some of the kind of empirical results that are there in terms of to what extent the computational mechanism of syntax is or is not captured by the current versions of the large language model. Of course, it's you're shooting a moving target. So whenever any empirical results is about some model that is going to be replaced by the next one pretty quickly. So this can only give you up to a certain amount of information. Eventually, you need a theoretical comparison, not just empirical tests, because So this is trying to shoot a moving target. No, it's not the way to approach the problem ultimately, but it gives some information. So I'll discuss some of that. But first, let's try to see, what is it that one could try to, how one could try to describe what is actually going on. So, working hypothesis that seems reasonable to assume is that what a large language model is doing is to perform a partial, as far as we know, and understanding exactly the boundaries of the question is part of the question, the solution to an inverse problem. And of course, inverse problems are incredibly hard to solve in general. And the inverse problem is coming from the fact that you have certain statistical proxy for syntactic relationship that exists in the structure of language. And typically your keys and queries vectors see this kind of like what terms are called for and will be called for by a certain element in the sentence, and will correlate, and one can be more precise about that, into certain particular syntactic structural relation like C command and other positions in the structure of the syntactic tree. And ultimately, the reason why you see these syntactic trees is this correlation. And so in a sense, you're conducting a very large parallel computing, searching through like a huge corpora of statistics of text for this kind of image, that is projected upon your semantic space from the structure, the actual structure of syntax. Okay, so this is a kind of hypothesis. So, more precisely trying to, describe it in terms that can be compared to, what one can model on the side of theoretical linguistics, is that you can think of the attention modules in transformer architectures as another example of this kind of Hopf algebra characters that describe a form of syntax semantic interface. So what we have been doing is something like this. You assume that you have a map from the lexical items to a semantic space. And this would be your embedding of the tokens into your vectors, in your vector space. And then you want to likely build a corresponding embedding of the syntactic objects with their structure inside the same semantic space. Okay, so the way you can think of this is that you can think of these attention matrices themselves as giving you a character of the Hopf algebra workspaces, where you just look at where attention is maximized with respect to fixing what the head now in the syntactic sense of your structure is and what it attends to. And so where it maximally attends to is, this is a way of rephrasing these results that have been found by Mann and others, is that, where it maximally attends to highly correlates to the actual syntactic relation that the syntactic head has to its complement in the phase part of the structure. And so you can, if you want to create describe a set of possible syntactic relation to be tested as being a relation between elements in your phrase, which would be the leaves of your syntactic tree, or the tokenization if we want to make it more compatible with the structure on the large language model. And this would be actual binary relation. So certain elements are in a certain syntactic relation or not. And what in doing this, effectively to compare this kind of binary relations dictated by syntax to the probabilistic relation dictated by where your attentions are optimized. I'm being imprecise here. I will actually come back to that more precisely, a bit later, where actually have to, where it becomes important to consider several layers of attention module and just not just a single one. And so at the moment, this is oversimplified, but it's just to describe the idea. So you can, for example, distinguish whether a certain kind of syntactic relation would be exactly detectable by these attention modules, whether it really correlates with what the attention is maximized. This or more generally would be only statistically approximately attention detectable over a sufficiently large corpus in an average sense. Okay, so if you think of it this way, then you can also do the same kind of analysis that we were discussing in terms of the decomposing over substructures with certain thresholds, or where you put some threshold on where this probability distribution of attention is localized, or where it's maximal, or where it's up, or where it's above a certain given threshold. And you have actually, part of the observation here is that if you make, in this Birkhoff decomposition, you make the quotient with respect to the contraction form of the quotient, then you can ensure that your syntactic head is not changing. So in particular, you can ensure that if you have maximized attention on certain part of the structure, you will not lose the optimization that you already have obtained at the previous. So you will get better. We will not get worse. But so you can look at chains of substructures where the attention gets at every step maximized, and try to correlate those to actual syntactic relations in the sense of the structure of the syntactic tree. And so you can look at it. So this Birkhoff factorization that we've been talking about in these various models of syntax semantic interface will give you chains of accessible terms that maximize the corresponding attention from the head, where that would locate the maximal, the optimal attention, and that is everywhere above a certain fixed threshold, and where all the quotients don't lose the optimality that's already achieved. Okay, so this is like a possible way in which one can investigate how this idea of locating syntactic trees inside the data of the attention modules can be broken down into more precise structures and substructures, and try to actually locate. I will come back in a moment to discuss this more. And you can let's say, correlate this to specific Boolean relations of particular that focus on particular type of syntactic relations one at a time, to kind of disentangle various types of syntactic relations that can be investigated independently. Okay. So then, if you want, the main question behind this idea of relating where the syntactic structures are encoded and where the computational mechanism of syntax is encoded is, in a sense, trying to actually pin down, at least, as I said, in a sense, it's difficult to pin down because these models keep changing. But on the other hand, you want to at least theoretically be able to pin down where the actual structure of syntax is encoded and where the calculations of syntax are happening and how. Okay, so before I get more into the actual architectures of this thing and trying to discuss where this one should look for these things, let me discuss some of these empirical evidence that I mentioned. So what the empirical evidence that I mean is tests that try to detect differences between the way that language is handled by language model and the way that language and specifically the calculations of syntax are handled by human beings. So there are in general different types of such empirical tests, and I'll talk about a few of them. So one is to actually try to detect in the structure of text a difference. So you compare text produced by human beings and text produced by large language models, and you try to have invariants that detect a difference. And the other is to actually devise specific examples of particular phenomena of syntax and try to see how humans and how large language model react to specific aspects of syntax. And another is to actually have more specific tests of how, for example, the large language model reacts to modifying prompts and getting results, which is what people in your lab are doing. So I'll say something about that too. Okay, so let's start with detecting differences in text. So you take a large set of text produced by humans, and you compare it with similar text generated by large language models. So, for example, part of what they've been using is text written for various archives produced by humans, like Wikipedia, and then making large language model produce text that starts with the same and then similar amounts of text and comparing them. So how do you compare them? So you need some kind of robust computational type of tools that you can apply and where you can measure the difference. So one of the results that seems interesting. This was applied to some specific language models, which I'll mention in a moment. But the idea was to use a kind of dimensionality counting. And there's various ways of doing dimensional countings, and this one was based on persistent homology dimension. And so I think you're going to say something more about that. So we'll give some details in his presentation. But basically, persistent homology is based on the idea that you have a certain set of data. They are data points, they're discrete data points embedded in some space, and usually some sufficiently large Euclidean space. And then you look at, you would like to see structure geometric structure in the data. For example, if we have a cloud of points like this, so they're all discrete points, but we sort of all see that they kind of lie around the circle, and that maybe they actually have other kind of smaller circle-like structures. Okay, and so the way to do this is, you look at your data at different scales, which means that you have a certain scale parameter, and whenever you have a bunch of points that are where all the distances in the ambient space are smaller than a certain scale, you fill in a simplex of that dimension. And this gives you a simplicial complex. And of course, it's a simplicial complex that changes with the scale. If I look at very small scale, well, at some point, necessarily, every point is isolated. So at the smallest possible scale, I don't see any topology. I just see a bunch of discrete points. But as my balls are growing, at some point they start to overlap, and then I'm going to see one skeleton, and then so eventually everything will be into one big ball, and so there will be no topology anymore. So that's why this is called persistent, because the interesting things are the parts where you do start to see some non-trivial generators. So usually first homology, sometimes some higher homologies, and these last for a sufficiently long amount of scales. So if they appear and disappear immediately, you kind of consider them noise or not particularly relevant structure. If they persist for a sufficiently long range of scales, then they are supposed to be actual structure in the data. And so there is one issue about this kind of topological data analysis, is that very often you do see structure and persistent structure, which means that there is something interesting in the way your data are shaped, but it's very difficult to have a specific interpretation of what you see means. So if you see non-trivial generators in persistent homology, sometimes you're lucky and you have an actual good theoretical interpretation for what these generators mean, and very often you don't. So that's one of the limitations. But okay, but generally, so this is kind of an example where you start to build your compass, and at the beginning you have just a lot of generators of H0. All the points are independent components. This one will go together until there's a single component. And then you will see, some maybe, for example, if you have some H1 generator that lasts a long time, those will be considered the important structure. The ones that appear and disappear are considered noise. So the way that these H0 components go together, they give you a tree-like structure, right? So whenever two components coalesce, you have 2 points that are joined together. So this give you have a tree-like structure that's associated to the H0 part of the homology, and that already gives some kind of indication of some kind of structure. Very often these trees correlate to some other tree that can be interpreted in some way, like that kind of phylogenetic trees of how things are related, or clustering trees of how things are related.
You just mean simplicial one complex. You mean one complex, simplicial one complex.
That's right. Well, yeah, but in general, you can think of it as a tree, like in the sense that whenever two coalesce, you make a cherry on your tree, and then when they coalesce with another component, you make it, and so you do get some kind of tree-like structure associated to the persistent diagram of the zero persistent homology. So there are two equivalent ways in which you see the persistent diagram represented. One is the one that I just described. So you have like your scales, here they're discretized, and you sort of look at for how long a certain cycle persists in your scale. So you get this kind of diagram. And of course, the other one is to just mark the beginning and the end of where it's born and where it dies, each cycle. And so if you draw your diagram like this, the points that are close to the diagonal are the noise, and the further away you are from the diagonal, the more significant is the structure that you see. So this is typical kind of things that you see. There's some kind of clustering of the H0 components, and some H1s that you can see some of them are more relevant, some are noise, and more rarely you have higher dimensional kind of structure in the data that's gives you some interesting information. Okay, so there's a way to associate a kind of dimension estimation to persistent homology of a data set. The idea is to think that your data points. So typically, the underlying idea in all of these kind of, I've already talked about it a while back when I was discussing, analyzing the data of syntactic parameters. Very often, the underlying idea for various forms of data analysis is that your data are actually sampled from some lower dimensional manifold inside your high dimensional space where the data points are represented. And so the underlying actual model is some Riemannian manifold embedded inside your ambient space. And the points are really sampled with respect to the volume form of your Riemannian manifold uniformly. But that is not known. So the manifold is part of what you would like to be able to infer from the data analysis. And of course, part of the dimension of this manifold will be visible by the distribution of points, in the sense that if things are sampled or uniformly from a manifold dimension D, you expect that the number of points in a ball will grow like R to the D. And so in one estimator of dimension that you associate to the persistent homology is you look at a certain degree of the homology, and in particular the case of components would be connected components, persistent connected component would be the degree 0. And then you look at all the generators that you have of the persistent homology, and you look at how much they persist. So you look exactly how far from the diagonal this point is. So you look at the length by which it persists, the difference between that and BERT in terms of the scale or the persistence scale, and you sum them up with some weight that's given by some exponent. And in particular, if you do it for the persistent connected components, this is like weighting the edges of this tree that you form that tells you how the connected components go together. And so there's some, in particular, one can extract some kind of growth rate from this estimation, which depends on the dimension. And so that's a way of seeing the dimension by looking at, estimating this kind of quantity and looking at how it's scale. I mean, assuming that it scales with the dimension. This would allow you to extract the dimension on a logarithmic scale in the number of points. So the estimator of dimension would be this kind of infimum over where this amount is founded. So if you want this extracted by this kind of formula, when the number of points is sufficiently large. Okay, so the kind of experiment that the kind of measurement that we've been doing about comparing text between the human generated text and large language model generated text is from texts which are not exceedingly long, about 300 tokens, but not too short. And you look at the embedding in your vector space this of the tokens. So you look at the corresponding vectors in your semantic space. And this is the ambient Euclidean space in which you do this computation of the persistent homology. And the result is that there is a very significant and systemic gap in dimension between the texts that are generated by the large language model and the texts that are generated by human, in the sense that the dimension is significantly lower for the texts that are artificial intelligence generated. And the only cases that are typically misclassified tend to happen on very short text, where either is classified either way. Otherwise, this is pretty consistent for everything. So what type? I'm gonna show in a moment more precisely the result that one gets. But what does it capture? I mean, this is of course one typical question when one has this type of data, topological data analysis. So you're seeing something. What is it that you're seeing? So here's so at least one can try to make some hypothesis about what it is that you're seeing, and if the hypothesis is correct, you should be able to see it in other ways too. That's the idea. So this is related to the positions of these embedding vectors inside your ambient space, right? That's what is measuring. And so this question is whether this dimension is in some way reflecting the hierarchical syntactic structures that go behind your combination, or your assignment words. And, in a sense, this reflects, this is a reasonable hypothesis to make, because these trees of persistent components usually correlate to some tree structure that's intrinsic in the data that you are describing. And so that would be natural to assume that the underlying tree structure is the actual syntactic object structure, and that this is reflecting a different level of depth, typically, of the syntactic trees that are handled by So this is like hypothesis that one can make about interpreting this gap. But so this is what we actually see. So this is a comparison for English text, the thing with various language models. In this case, GPT-1, GPT-2, other one, and this is the average dimension with the corresponding magnifier for the AI generated text and for the human generated text. This this parameter alpha, you can wonder how much it affects the results if you let this parameter alpha vary. I mean, it doesn't, in the sense that the gap is persistent, so it kind of has an effect on this, some effect on this dimension that you analyze, that you compute, but the gap is consistent for varying this parameter alpha. And the other thing that you observe is that this is not language dependent. So if this has been run on a number of different languages, the actual dimensionality is somewhat language dependent. And this is maybe not surprising, because languages have different syntactic parameters, and the kind of syntactic structures that will occur are different. And that's your point, the fact that externalization imposes different filters on according to language. So you do expect to see some slight effect. The effect is not extremely significant, but it does have a variation in dimension. But the difference, the gap between the human-generated text and the AI-generated text is pretty much significantly consistent across languages. So this seems to be one indication that the handling of syntax by large language model is not the same as the handling of syntax by humans. Okay, let's look at some other kind of empirical evidence that compares more directly the handling of syntax by specifically, yes.
If you go back to the slide with the three models, does more parameters actually make it worse? The dimensionality is actually reduced when you add more. For GPT-2 and GPT 3.5, I thought I saw less dimensions if you go one further.
Yeah, this one, yeah. Yeah, that's right. So okay, this is not I think well understood why there's some variation between these different models of large language models. And also, I don't know, I don't think that this is being now applied to the more recent ones. So whether there's a further variation after GPT 3.5 to the more recent ones. So there is indeed some kind of model dependent factors which might depend on different training of models. I don't think that this has been that this is well understood at this point why this gap. But okay, let's then see what else one can say about the specific handling of syntax by large language models. So there is a database of syntactic examples. So these are all examples that are collected from one of the main journals of theoretical linguistics, which is Linguistic Inquiry, over the span of 10 years. And the database is organized so that one can subdivide it into specific syntactic phenomena that they illustrate. And these examples include both positive examples. So, for example, they illustrate how a certain syntactic phenomenon works in some particular languages, and also negative examples. So examples that violate certain syntactic rules, and that are therefore not syntactically viable. And so these examples have been tested on humans and on machines. So first of all, there's the two slightly different kind of tests that one can do on this kind of syntactic examples, and they're not exactly the same thing. So one test is acceptability, and another test is grammaticality. So grammaticality is what a linguist will tell you. This is consistent with the syntactic parameters of this particular language is grammatical according to the syntax. For example, you have violation of data roles assignment, or violation of head and complement assignment, or violation of most. These would be things that can be violated across languages, or violation of more specific syntactic structures of one particular language. Acceptability is more of a nuanced phenomenon in which you ask a native speaker of a language the degree of acceptability of a certain sentence. Right? So someone can say, okay, it doesn't sound so awkward, but maybe it's probably right. Or nah, no. And so it's more like a user value judgment. So first of all, there was an investigation, which is this first paper that was just about detecting the consistency of judgment across human users, and how much delta there is in the appreciation of acceptability over these all examples, where you actually know from each of these examples from the linguistic perspective whether the grammaticality holds, but the issue is how they are acceptable, they are perceived by human users. And then there's the systematic testing of these over large language models. Okay, so there's some specific discussion of these acceptability judgments. There are like three kinds of acceptability judgments that are measured in human users. One of them is like a magnitude estimation, where you make a certain size of how on or off you are, and you judge in multiples of that size. So like very okay, very not okay, and then some. So there's like 7 steps. There's like. So one is just magnitude estimation, which is, and another is on a 7-point scale, where it's like very bad, very good, and in between, and somewhat in between. And then there is this kind of 2 alternative force choice, where you have pairs of examples that have a very similar syntactic structure. One of them is correct, and the other one is wrong because it violates one very specific syntactic rule. So it's like a very controlled experiment. They look very similar, but one of them is, and then your force choice is you have to say which one of the 2 is correct. Okay, so and the thing is that over human tests, this is very consistent. So there's a 95% agreement with the grammaticality test, and the maximal error that happen is around 5% over. Right? So there's pretty consistent agreement across human judgment of the syntactic viability of this test. Okay, so now what about the large language model? So one test that uses the same database on large language models was conducted in 2021 on BERT, which is this bidirectional, with this bidirectional architecture. And I'll say in a moment about this acceptability criterion, but the basic result is that on judging these pairs, neural pairs correctly, the BERT scores only approximately 30%. And this is just barely around the same as the simple trigram statistical models of Shannon of the 1940s. And so this was tested on a collection of more than 4,000 sentences and 2,000 comparative pairs, and compared with the human judgment data. So this is kind of the test. So one thing measured is this correlation coefficient scores, which compares true positive, false positive, true negatives, false negatives, and look at the occurrence of all of these things. But so basically, this is tested over dividing the example into specific aspects of syntax. And this is the pretty consistent human evaluation score. And this is where the different versions of BERT were performing compared to human. And this is done for even more larger number of subcategories of syntactic phenomena. And again, some of them are extremely poor. Some of them are somewhat better. But again, overall, this is the level of the human handling of syntax. And this is what else you see from the judgment of acceptability in this model. So some of them are very significantly lower than the human handling.
Why does case make such a big difference in some of these?
Yeah, so why some aspects of syntax are so poorly are handling so poorly compared to others is again not well understood, right? But there are very significant differences, obviously. So there's no good theoretical explanation for why.
And I'm asking if so the three labels, it says uncased.
Yeah, so these are three very different versions of the BERT large language model that they tested. And they, so in some cases they perform similarly, in other cases they don't. Again, the difference in response between different models, I don't think it's well understood why that's the case. Yeah, so one thing that's interesting here is that there is one case in which you can say something about the difference. One of the version was fine-tuned on a specific syntax database. So one of the versions of the large language model that they tested was specifically fine-tuned for specific syntactic phenomena, but it was still, in some cases, still performing much lower than the human handling. And so this is again the results is that this would correctly evaluate about 31% of the cases, and the just basic trigram, Shannon trigram model would evaluate about 30%. Okay. So that's the conclusion one can draw from this. So there's another kind of test that was done about the handling of syntax, independently of the one that I just described, with a different method of handling of specific syntactic phenomena by large language models. So here they actually focused on 8 specific syntactic phenomena, syntactic constructions, and which have the advantage that they're all easy to decide whether they are syntactically correct or not, and they're all don't depend on context. So you don't need to you're not affected by your in context, your specific sentence in context, whether the syntacticality of the is the grammaticality is very easy to discern without any context information. And so each phenomenon was tested with 10 sentences, 5 of which were grammatical and 5 ungrammatical. And again, in a way that the ungrammatical one would violate just one specific rule of English syntax. It was specifically done with only with. And okay, the prompt used was this one, is the following sentence grammatically correct in English. Okay, that's a question of whether we can manipulate prompts. I'll come to that later. Okay, so this was tested on 2 versions of GPT-3 and GPT in 2022 and last year. And again, it's compared with judgments from humans on the same subject. So here's something that happens that seems kind of interesting. So the grammatical ones are pretty much caught with reasonable agreement, and with agreement that has been performs better. Certain models are going to perform better than others on guessing the correct one. At the same time, they perform much worse at guessing the non-grammatical ones. So the precision in guessing the grammatical ones comes with the widening imprecision in guessing, in correctly identifying the non-grammatical ones. And okay, so this is the first observation, right? That there's a very big gap between being able to identify the ones that are correct and being able to identify the ones that are not correct, and they are inversely proportional. And then overall, dividing by these 8 different syntactic phenomena that are being analyzed, is the record for guessing the grammatical ones and the non-grammatical ones, and the mean results between the two. So again, some phenomena are very poorly detected, and others are better detected. And again, overall, the correct ones are better detected than the non-grammatical ones. Also, there's a very significant response instability, which means that if you ask that you present the same example over and over again, the result varies. And the result varies, again, differently according to the grammatical and the non-grammatical ones. And how much repeating the same example will affect the results, or will increase accuracy or not, again, sort of changes significantly. The mean accuracy is in some cases slightly increasing, some cases more increasing, some cases decreasing. And if you compare with human judgment, you find that the human judgment is more or less stable across the grammatical and non-grammatical examples. Humans also have a slight more difficulty detecting the non-grammatical example than the grammatical ones, but the difference is rather minimal, whereas the difference in the large language model is extremely significant. And again, by specific syntactic phenomena, the gap between the human guessing and of course, it turns out that the most difficult one is also the most difficult one for humans, which is the center embedding kind of but in all the other ones, there is a significant gap. And the likelihood of oscillations in the response is almost none for human, and is significant for the large language models. Okay, so I'm gonna continue next time, but for now, where are we? So, pessimistic viewpoint, right? We are witnessing the most extensive and most expensive experiment ever conducted to show that Zellig Harris model of syntax is not accurate. So the kind of less pessimistic viewpoint is that one can still ask what additional information about this question about solving this inverse problem of syntax from semantic spaces can be derived from using large language model as an experimental apparatus for investigating this question. So I will continue next time with this.
Is it pessimistic or optimistic?
So now I leave it up to you which one you want to choose.